everybody. This is the qualitative example problem that's going to go along with your Unit 3 big picture. So hopefully you were either in class to watch the big picture or you already saw the video for the big picture before this point. You pretty much have to have those big picture notes for any of this to make sense. But what you should be noticing is that the same pattern that we had for Unit 2 is the same pattern that we're going to have for Unit 3, where we have kind of all of our big picture notes that look at things qualitatively and quantitatively. You get the equation, but then we ultimately start practicing qualitatively first, and then we'll move on to the quantitative side. So we're going to start with the qualitative graphing. Now, one of the things that came out from the big picture is that, yes, the slope of position versus time gives us velocity, but now we know that the velocity is changing. And from that changing velocity, we now get linear velocity versus time graphs, and then the slope of the velocity versus time graph is then acceleration. So that means that we can actually have a position versus time, velocity versus time, and acceleration versus time graph. And the fun thing about the acceleration versus time graph is since we're dealing with a uniform acceleration, same rules that you had in Unit 2 apply to the acceleration because you're only going to have horizontal lines. That's different though for the velocity. So let's go ahead and first, take a look at the written description and then tackle that velocity versus time. So the questions that you see here, so create the qualitative written description, V versus T and A versus T, those are the very standard things that you're going to do with your qualitative problems. So in your notebook, because I will be checking when I do a notebook check, I do want to see this example problem there. And do notice there are 4 sections within this example problem. So at this point, you want to pause the video and come back in once you've copied down this position versus time. All right, so now that you're back, the first thing that we're going to do with the written description is obviously say, where does the object start? And the object starts at the reference point. Then we want to say, just as in Unit 2, first of all, is it moving? The answer is yes. And then where is it going? Well, we know that the object is going away from the reference point. So that means regardless of how we're going away, all of those values are going to be positive, meaning that it's going to be in the upper quadrant of that V versus T graph. So we're going away, so everything is positive. And then how are we going away? Well, when we look at the steepness, are we going from less steep to more steep or more steep to less steep? And we're seeing that we're going from way more steep to less. So the steeper you are, the faster you're going because that's the more distance you're traveling in the same amount of time. So what we're doing here is we're going from fast to slow and we're going away. And if we're going from fast to slow, that means that our values are very big and then they're getting smaller. So just like if you were driving, maybe you're going 65 down to like 25. But what we see happening in this section 2 is actually nothing. The position isn't changing. So the object has stopped. The velocity is 0. So the object stops for some time and then decides that it's going to head back toward the reference point. So whenever you would take the slope of this line, you know that we're going to do it multiple times. We're going to get negative numbers. And how are we moving away? Well, here we see that we're going from less steep, so not really traveling too much distance, to very steep. So that means we have to be going from slow to fast towards. And then this last section, well, that's just Unit 2. Unit 2 doesn't go away because now the object speeds away from the reference point, going at a very, very, very fast constant velocity. You do have to mention that it is constant. So that's what you'll see when we go down to my work here. So object starts at the reference point, goes away from fast to slow, then it stops, then it goes towards from slow to fast. And then this last part, we want to say, yes, we're going away very quickly, and we're going away at that constant velocity. You do have to indicate the type of motion. So in section 1 and 3, we said, hey, fast to slow or slow to fast. That indicated an acceleration, whereas here we're now indicating that CV. And we also want to note that it's only going at that constant velocity for a very, very short amount of time. So then when we go ahead and make the velocity versus time graph, the first thing is that we indicated that we are going away from the reference point. So automatically we are working in the positive quadrant, regardless of how the numbers are changing. But if the numbers are changing from fast to slow, then we have to be going from big number to small number. And since this x-axis is representing our 0, then any number way above is going to be a really high number. And then as we get closer and closer to 0, those are our lower numbers. So we start fast, get slow, so we go big number to small number. Then we stop, so velocity is 0. And then we go towards the reference point. So now we are in that negative. And if we're going from slow to fast, then we're going from small number to big number. So that's the same thing we're doing here. We're starting very close to 0, which will have the small numbers, and then our big numbers are going down here as we progress downwards on that graph. Then once again, we go away, so we pop back up into that positive quadrant, and we're going at a very fast velocity, so it's going to be a really big number, so that's why I have it in the highest position, and it's a constant velocity, so now we're back to a horizontal line. Then the last thing is that we know that the slope of the velocity versus time graph is acceleration. So when you make the acceleration graph, the only thing that you should be looking at is the v versus t. Acceleration is not based off of position versus time. It is only based off of velocity versus time, as told by the definition of acceleration being a change in velocity divided by time. So we're going to end up doing the same thing as before. You know, is the slope of this line going to be positive or negative? Or we can say, is the object, or is it going towards or away from the reference point? Well, it's going towards, but more so we want to say, hey, the slope of this line is negative. Because if you were to do 0 minus 5, you're going to get a negative number. So acceleration is negative. You took the slope of a linear line, meaning that no matter what 2 points you would have picked, you would have gotten the same number. So we have a horizontal line for acceleration. If your object is not moving, meaning velocity is 0, then acceleration has to be 0. If we look at this portion of the graph and we say, okay, is the slope going to be positive or negative? The answer is negative. If you do -5 minus 0, still getting a negative number. So that's why we have it down here. And if you're at a constant velocity, it's not changing, then you can't possibly have an acceleration. This would be as if you sped up to whatever velocity you would be going on the highway, and then you hit cruise control. If you're in cruise control, you have no acceleration. You're just cruising at that same constant speed. So it's kind of nice when you get a constant velocity because A is just 0. And that's the progression that we should have. Position versus time gets us a written description. Written description brings us to the velocity versus time, and then velocity brings us to acceleration. And notice that many of the same questions that we had in Unit 2, we now have in Unit 3. We're just going to ask twice in order to create the acceleration versus time instead of just asking once like we had to do before. All right, hope this helped. Make sure that you do your ticket out the door and you submit that to Canvas by midnight tonight.